Good morning. We have a midterm exam tomorrow. I will send an announcement by Piazza and email with all the details, but just to give you a heads up, we're actually going to use two different locations for the exam for two different groups of students. So we will let you know based on your name or your ID which one you should go to. The exam is closed books, closed notes, except that you can bring one sheet of paper where you can write whatever you want on. Okay? One regular 8.5 by 11 sheet of paper you can write on either side. You can print, you can type, you can microfiche, anything you want. That should be more than enough for any formulas that you think you may need that you don't remember. Yeah. No calculator needed or allowed. Okay. I put an example exam online from a couple of years ago. No promises it'll be the same questions. In fact, almost promises it will not be the same questions. But the reason I did it is to kind of tell you what kind of questions I like to ask. I don't like to ask busy questions. We have to do a lot of calculations. That doesn't make sense in an exam when you're under time pressure. I don't ask you to prove anything, at least not in the mathematical sense of proof, but you can argue for things. And I try to ask questions that go to the basic understanding of the material. So I try to make it such that if you feel good about the material, if you really think you know it, then you will do well. I try. The exam will not be the full 3 hours that we or 2.5 hours, whatever it is that we allotted to it. It would be much less than that, probably an hour and a half. But I will send you all of that clearly in writing, probably sometime today once we finalize it. Any questions about the exam? Okay. Next, I have a correction to make. I told you something that isn't true, and I actually told it to last year's class too, so I have to get a hold of them and correct them as well. We were talking about correlations. Start with covariance. We said that covariance of ax plus b cx plus d. Do you remember what that is? Covariance is invariant under shift, so we can get rid of the b and the d, and the a and the c come straight out. So it becomes a times c times the covariant of x and y. And then if you look at correlation, correlation is the same as covariance, except it's normalized by the standard error of both participants.
Would that be CY plus
C, y, yeah. Thank you. Correlation of ax plus b cy plus d is I don't want you to memorize the formulas, I want you to understand them. The formula is just an expression of your understanding, not something to memorize. Correlations are invariant under shift and scale, right? This is a shift, this is a scale. They are invariant under a shift and scale of either or both of the parameters. Okay? So much is true. So what we would have here is just a correlation of x and y with a slight complication that if these are not shifts but inversions, then the sign of the correlation changes. If you invert once and you invert again, if you invert both x and y, then it changes twice, so it doesn't change. So what you have to do is put AC here, A times C with the word sign in front of it. So if the product of the two is negative, it inverts the sign, otherwise it doesn't. So far, so good. I then went on to claim that because correlation is invariant under shift and scale of either variable, that if you rotate the axes, that corresponds to a coordinated linear coordinated shift and scale of x and y. If you have ever seen a matrix, a rotation matrix, you'll see that 1x, I'll write it here, rotation, x and y go to x prime and y prime. And the way they do that, so you have x and y here, and I may need your help, William, but I think this is cosine theta, and sine, negative sine, and sine. This gives you x bar, y bar. Rotation can be thought of as deriving x bar as cosine theta x minus sine theta y. Cosine theta times x minus sine theta times y. The important thing is these are constants. They correspond to this a and c here. They are linear combination of x and y. And I went on to argue that because any rotation by any fixed amount can be written this way, the x and y's are, the new x and y's are linear combinations of the old x and y's, which is true, and therefore the rotation doesn't change, which is false. That's where I made a mistake, and William Shargin kindly pointed it out to me and found the mistake. Pointed out that correlation is a continuous function, the way it's defined, and it doesn't make sense for it to, when you have a continuous function and have a discontinuity, the point in between would be undefined, as opposed to defined with the value of 0, which is what I suggested. So this led, forget the details, the important thing is correlation is not invariant under rotation. In fact, if you rotate even a little bit, it does change. How do we understand it? How do I understand it here? Let's look at the y is sine theta times x plus cosine theta times y. So x bar is a linear combination of x and y. Y bar is a linear combination of x and y. So we transformed the logical flaw in my argument was that it's true that correlation is invariant as long as you do a linear transformation of every variable on its own. So if x is shifted and scaled, it doesn't affect anything. If y is shifted and scaled, it doesn't affect anything. If they're both shifted and scaled, it doesn't affect anything. But if you're creating linear combinations of the old coordinates, then the vectors that define them, these coefficients, it starts mattering what the angle between these vectors are. You can take it to an extreme in saying if the new x and new y have the same, if x bar is some a times x plus b times y, and y bar is a plus epsilon times x plus a b times y. By making epsilon very small, you have now made these two almost the same. In other words, highly correlated. All right, take-home message. Correlation is not invariant under rotation. It is not invariant under a transformation of the coordinate system. it is invariant under linear shifting and scaling of each variable alone. Yeah?
So I guess another way to look at it is as you rotate, if you're doing a line of best fit, your slope could become infinity, right? And then your residuals do really wacky things when your slope is infinity, you're trying to measure.
That is not, that is true, but I don't think that's the right explanation here, because yes, as you rotate and you get to a point where the variance of one of the two sides gets close to 0, things can get wacky.
Yeah.
But this happens even when it doesn't get to 0, and it happens even when you're not aligned with the axes. So a different way of looking at it is to say a reorganization of the coordinate system, a change in the coordinate system can correspond to taking your Euclidean space and squishing it. You can turn it, but you can also squish it, which changes our notion of correlation between points. Okay, so I'll correct it in my notes, and thanks again to William for pointing it out. This is the best thing you can do for me in this course. Find mistakes in what I say and come show them to me. So I encourage you to do that. Well, it's easy to find mistakes in what I say. It's harder to find mistakes in what I write, because that is subject to a little more careful. So find especially mistakes in what I write, but any mistake would be appreciated. Okay, the next topic I want to cover is still within linear regression and linear learning. And some of you already jumped the gun and discussed it with me online on Piazza, which is great. But planned for today. And the idea is to say that linear regression, or in a linear model, is called linear not because it is linear in the original covariates, in the original inputs. It is called linear because it is linear in the parameters. What I mean by that is that if we say that E of y given x1 through xp no, E of y as function of x1 through xp is expressed in a linear model. That would include cases where we have complicated function of the x1 through xp. So we looked at the case where E of y was expressed as sum of beta j xj. But we can also look at cases where E of y is expressed as sum of beta j, some fancy fj function of x1 through xp. You can have arbitrarily complex functions here. Once you are given the design matrix, your training data, you can apply these functions to the training data and generate new covariates or new features. Let's call these features. Or new covariates. Or we call them in AI intermediate representations. So here's, this is, if you do that, this is still a linear model. And we can still do linear regression to fit the values of the betas. What's linear here is what's happening here. The dependence on the original axis does not have to be linear. So, for example, one very common kind of regression is to say you have only one covariate, x1, and you say that f1 is x1, f2 of x1 is x1 squared, all the way to fp, we call it p, fp is x1 to the power of p. And now you plug it in here, and you have a way of expressing a polynomial in x1. This is called polynomial regression. Polynomial regression is still linear regression. What's important is that you can calculate in advance the value of these new covariates, and then the fitting problem is still a linear fitting problem. And therefore, it has a nice closed form solution in the vanilla case. Suppose you have two covariates, x1 and x2. You could have the following functions, x1, x2, x1 times x2, x1 to the 7th times x2 to, how about square root of x2? How about sine of x1 plus, you got it, x2 over x1. Arbitrary functions. Which means linear regression doesn't restrict your ability to express what you think are, well, it does restrict it, but it does not restrict it as strongly to restrict your ability to express what you think are the true relationships between the inputs and the outputs. If you believe that the output depends on the square of the temperature, that does not rule out a linear model. You just square the temperature. Let's put it in as a covariate. Okay. Any questions about that? I want to emphasize, go back to something we discussed already, but spend a little more time on it, and then move on to neural networks, which will not be on the exam. Okay. This line stands for, this is an array, a vector of values from beta 0 to beta p. This is how many machine learning problems start. Minimizing parameter over something, and that something is usually called a loss function. In our case, we said we chose a loss function that is squared residuals. I'll write it here as squared residuals. This looks tiny and innocent, but really inside this thing, there are lots of things. To calculate those lost residuals, you need to know xi, right? To calculate epsilon I, you need to know xi, you need to know yi, and you need to know the betas. In other words, you need to know all the parameters of the model, and you need to know the labeled training example. All the xi's, all the covariates for example I, and the label for example I. But I'm going to keep it like this because this is conceptually simpler. It says what I'm doing is minimizing some particular combination of the residuals. And then I'm going to add something else. This can be thought of as how well does the model, or do the parameters, fit the data. All right, how well does this model, by model I mean this particular combination of model with these betas, fit the data? Or alternatively explain the data. The second part is going to be how simple is this explanation, which here we're going to measure with some kind of norm on the betas, with some measure of the how big the betas are, how many of them there are. So this would be some measures of the betas. I'll make it beta to the power of p, and maybe I'll make it square root of p, square root of p. This is how simple is the model. Again, as a function of the betas. This is what you would typically find in an optimization problem in machine learning. You would find two components. One of them deals with how well the model describes the data or explains the data. The other one deals with how simple that model is. This is Occam's razor all over again. We're trying to trade off simplicity with goodness of fit. You have a choice. In fact, you have two choices. You have a choice. Actually, you have three choices. Three choices. The first choice is, how do you define goodness of fit? How well does it fit the data? We chose to square the residuals here. There are many other choices. This choice corresponds to assuming that the data was generated by taking the mean and drawing a random Gaussian point around it. So Gaussian residuals. If you assume that they're actually drawn as a binomial distribution, you get a log version, which leads to logistic regression, which is also a form of linear regression or linear model. You make another assumption, you get something else. The second choice you have is, how do you measure simplicity? Do you want the betas to be small? Maybe. Maybe you want them all to be small. You don't want any beta to be too big. I mean, that's your notion of simplicity. Or other than simplicity, usually we prefer simple models, but you might have other reasons to prefer other kinds of models. So this gives you preference to some models over others. This is our soft bias. You could also measure how many of the betas are non-zero. So that corresponds more to our notion of scientific simplicity, a simpler explanation involving fewer factors. The third choice you have is, how do you combine the two? Usually we put a lambda here, which is a positive number, and we use it as a knob. And you could think of different ways of choosing that lambda. The most common used method is by cross-validation, by seeing which value of lambda ends up performing best on held out or left out data. We will talk about other ways. I think we already talked about other ways of choosing that. Let me reiterate something about this, since it's very commonly used. This is called LP. This is the norm, the P norm of the vector of betas. And the norm that I think I mentioned to you appeals to me the most is the L0 norm. The L0 norm effectively measures how many of the betas are non-zero. So it tries to minimize the number of ones that are non-zero. The problem with it is that this function, this combined function, specifically this part, when you use the L0 norm, is a non-convex function, which means it is hard to optimize. When you use L1 norm, it's a reasonably good approximation of the L0 norm, but it is computationally feasible. It's still a convex problem. So we'll say that LP is convex. It's a convex problem for P greater than or equal 1. So you can use 1, 1.1, 1.5, or 2. Anything less than that would be computationally difficult to optimize. I think I mentioned that L1, using L1 is called the lasso. Losing L2 is called ridge regression. And using L0 is called subset regression. Subset selection or subset regression. This is called subset regression because if you really want to solve it optimally, and we don't have an efficient way of doing that, you can just systematically go over all possible subsets of the covariates, fit them using a simple ordinary least square fit, and then plug the values into here and into here, which is here would be simply the number of non-zero covariates, and compare them. So you can find the optimal solution, but you need to go over all possible subsets of covariates, and that would be an exponential number.
Do you ever combine multiple LP norms?
Yeah, very common. So if you combine L1 and L2, this would look like beta bar optimal of some sort. It would be argmax, argmin of some loss function. I'll write it as a loss function of the residuals. So this is this plus lambda 1 times the sum of beta j's. So this is the L1. Plus lambda 2 times the sum of bj squared. And I might do this. I think the normal ridge regression does not do this. If you do that, so now you have two parameters, you have more choices. This is called an elastic net. And the reason is, this is worth pointing out, when you do lasso, and you trace the likelihood function in parameter space, the equi-lines look like this. So these lines all correspond to the same likelihood function. These are the same, these are like equal height features. This is lasso. When you use ridge regression, they are round. And when you use a combination of the two, you get a combination of round and the sharp edges. So you get these sort of semi-sharp edges, but they're kind of rounded. So by tweaking these parameters, you get to change that. It's an elastic net. You know, its elasticity is expressed in the lambdas. The point is, these are all design choices. They're not determined mathematically by the data. They're all part of your definition of soft bias. Yeah.
Why isn't the square root intersected?
Why isn't the square root there? I don't know. You know, I like to think of LP as bringing it to the same dimension as the original beta. For some reason, I do not think they do that in ridge regression. Maybe because it's a analytically easier thing to deal with without the square root. I don't know why. You could. I mean, there's nothing that prevents you from doing that. It would be a somewhat different condition because you're weighing differently this component than say this component to this component. Even if this parameter is just a constant or a multiplicative constant, this would be different. But I'm guessing that it's just analytically the thing that's easier to solve. No, let me give you a slightly better answer. There's another interpretation for this. Interpretation for this is that if the parameters were chosen from some other distribution, a prior distribution over parameters, we will talk about distributions over the parameters when we talk about Bayes reasoning, then this corresponds to the assumption that they came from a Gaussian prior. So this is a Gaussian prior over the betas. So assuming a Gaussian prior leads to this kind of a, this is called the penalty term. So just like this is called the loss function, all these terms, either this one or both of these, are called penalty term or terms, or you might call them regularization terms. This entire idea of combining the two is called regularization. So you can think of regularization as a quantitative version of Occam's razor. I won't write the whole thing. Quantitative generalization of Occam's razor. And these are called the regularization terms or the regularizers. When are they needed? Typically when P is larger than N. Remember, P is the number of covariates. N is the number of data points. When P is larger than N, the normal formula for finding the closed form ordinary least square solution involves inverting something like this. XDX. XDX is, so inverting this. X is a N by P. XT is a P by N. So this is P by N times N by P. This gives us a P by P matrix. XTX is a P by P matrix. If N is smaller than P, then the rank of this matrix cannot be larger than N, which means it's smaller than P, which means it's not full rank, which means it's not invertible. So typically when P is greater than N, usually say much greater than N, you definitely want regularization. When it's even a little bit greater than N, you're not going to have a solution unless you do some kind of regularization. Even when N is greater than P, you might want regularization. Now it's not an algebraic necessity, but it's a modeling, it's a reasonable modeling consideration. You know, if you have N exactly equals P, if they're in general position, chances are you can invert the matrix, but you shouldn't trust your answer too much. You have an average of one data point per parameter. That's not, you know, in hand waving speaking, the variance of your estimate would be quite large. The solution would be very, very sensitive to small changes in the data. Regularization tends to stabilize the answer, to shrink it towards a more stable solution that is not as influenced by random changes in your training data. If you have N much larger than P, maybe you don't need regularization. So another way of thinking about it is that regularization reduces the variance of your solution. By the variance of the solution, I mean the following thing. You have only a single data set in a particular case, but you imagine that every day your data set changes. Imagine when you analyze the quality of your solution, of your method, imagine that today you have one sample on which to train, that tomorrow you will have a different sample that was drawn from the same distribution, but was just a different sample. And you apply the same procedure, and you get a model out. And you do it day after day after day, and then you ask yourself, how different are the models that I get at the end of this? How different are they from one another on average? If they tend to be quite different, just because of the random fluctuations of the luck of the draw, then we say that the model has high variance. Regularization reduces that variance. It makes it less sensitive to changes in the input. At what cost? There's no free lunch, right? At what cost? It's at the cost of increased bias. And here I use the term bias to mean both statistical bias and inductive bias. I think I pointed out to you that they're not quite the same thing, but they are related. In statistical terminology, we will say that the regularizes reduces variance, and almost always when you reduce variance, you increase bias. But the bias here is not necessarily bad. And in machine learning, bias is definitely not a bad thing. Inductive bias is a necessary thing. It's just a question of what bias you're using, and do you believe that bias? So this goes to your choice of P here, or you can have a different measure here that's not a norm, that's some other penalty term. So this is when, even when n is greater than P, even when it's much bigger than P. When it's a little bigger than P, or exactly P, the variance is very large. You definitely want regularization. When it's much larger than P, then introduce the bias if you feel that it's a good bias. If you have a good feeling, you believe that it's the right thing. It's like everything else in machine learning. If you have a lot of data, n is the amount of data you have, right? N is the amount of data you have. P is supposedly the complexity of the solution space. Right? Maybe the size of the hypothesis, related to the size of the hypothesis space. If you have a lot of data relative to the complexity or size of the hypothesis space, n is much larger than P, you can afford to get away with fewer assumptions. If you have less data, n is smaller, close to P, or even smaller than P itself, then you're in a sparse situation. You have many more possibilities than you have data to restrain it. You need strong constraints. You need regularization. Question? Yeah?
Would you ever use P as a knob? Like just let your...
Well, to use P, would you ever use P as a knob? To use P as a knob means that you have to order your covariates and decide which ones are more important, which ones are less important. Right? A priori.
In terms of the loss.
Oh, I'm sorry. This P. Yeah, there are too many P's here. I think that Elastic Net effectively does that. But did anybody ever use it as a parameter? That's an interesting question. I'm guessing somebody thought about it. One thing you need to think about is how do you optimize over it, since the dependence on it is kind of funky. It's through an exponentiation. You need to think if you have, if you're using gradient descent, sure, you can always take derivatives. If you're using something else, maybe not. Yeah. Yes?
Smaller similar solutions for beta means less variance. Can you explain why is that?
I can try. I'm not sure it's the best explanation, but I'll give you my intuitive explanation. You can think of this part as taking the playing fields of betas. Let's say betas are playing in a level playing field. It has as many dimensions as the number of betas, as P, but you can imagine there's 2 dimensions. And making it not an even playing field. Creating preference or attraction towards a relatively small neighborhood where the betas are small, right? So it draws, or here's a slightly different way of explaining it, might be better. Here's a space of betas. I'll draw it in 2 dimensions just because I can only draw in 2 dimensions. Beta 1 and beta 2. If you don't constrain, if you don't use regularization, the solution might fall anywhere. For any particular data set, the solution might have fallen here, but with the regularization, it would be drawn towards the origin. Right? Now imagine lots of different data sets. There's another one that with no regularization, the solution would fall here, but with a regularization, it would be drawn towards the origin. And in fact, that how much it's drawn depends on the lambda, on the knob. So now imagine the space of all solutions before you put in regularization. And now you put in regularization by taking that lambda and gradually increasing it from 0 up. As you increase it, the solutions go towards the origin, right? Now, what is the variance in that space? It's the variance of the distribution of the different solutions. If you're shrinking it towards the center, the variance goes down. Sir?
When would we want to use each of these 4 different types of regularization that you've introduced?
When would we?
Yeah, under what different use cases would we want to choose each of these from these 4?
How do you choose among them?
Yeah.
The choice doesn't correspond as much to prior notions about the domain the way they do in other cases we discussed. So in decision trees, I ask you, when would you want to choose a decision tree? And the answer is if you believe that the problem depends on a small number of covariates. Even though you have 100 of them, it only depends on 2 or 3. You just don't know which. 2 or 3 or 5 or 10, but small. In the case of linear regression, when would you choose linear regression is when you believe that the answer depends more or less linearly on some function of the original covariates, which you can pre-specify. Now, if you ask when would I choose L2 or L1 or L0 or any other L, how do I relate that to what I believe about the domain? I don't have a direct answer. I do for some case. The L0 is a very clear answer. It's when I believe that the answer depends linearly on a small number of covariates, right? Linearly, that's why I'm using a linear model, and small number of covariates because L0 pushes me towards dependence on a small number of covariates. If you believe that's true, then you should probably use lasso rather than L0. Lasso gives a result that's very similar to L0. In fact, what lasso tends to do is it orders the covariates in order of importance. And then it gives you what's called a path solution that says, if you're willing to accept 7 covariates, here are the best 7 covariates to use. If you're willing to use only 6 covariates, your fit would be slightly worse. I'll show you how much worse, but drop this one of the 7, and then drop that one of the 7, and then drop that one of the 7. It's not guaranteed to be optimal the way L0 is optimal in that regard, but it's a pretty good approximation. On the positive side, it's computationally fairly easy, and there are packages that implement it. So I would say if you believe that the solution should be sparse, you should go for the L1 or L0, and for computational reasons, you should go with L1. When would you prefer L2?
I heard that the L2 is usually used to avoid overfitting, but I don't know why.
Well, all of them are used to avoid overfitting. Regularization is about avoiding overfitting. Yeah, I'll tell you when you use L2. L2 tends to result in coefficients that are very small. That's a big difference between L1 and L2. If what you care about is minimizing this, you get few covariates, few non-zero betas. If what you care about is minimizing this, whether with the square root or without, it doesn't matter, what you get is lots of small betas. So, to answer your question, if you believe that your answer depends on all or most of the covariates, but each one in a small way, that it doesn't depend on any one particular covariate in a huge way, because what the squaring does is it overemphasizes the dependence on one of these, on any number of these betas that want to be big, right? It doesn't want them to be big. It wants to squash them down. In fact, you can exaggerate this more by turning it from L2 to L3 or L4 or L5. If you take it to a large P, large norm, you are severely penalizing very large betas, and that will really push all the betas to be small. Remember what happens in the limit? L infinity? You remember what L infinity is? L infinity is the maximum over beta I. So it's an extreme case where you care only about the largest and you don't care about the others. L10 cares a lot more about the large ones than about the small ones, but still cares somewhat about the small ones. So I actually have a better answer than I thought I did. If you think the dependence is on small number of covariates, think lasso. If you think the dependence is on lots of covariates, but not too much on any one of them, think ridge regression, that's L2. And if you're not sure, you do elastic nets. And a lot of people use elastic nets, and they work very nicely. And you let the data, by cross-validation, determine the values of the conversion factors, the lambda 1 and lambda 2. All right, before we move on to neural networks, I thought I should give you an opportunity to ask questions about any of the material that we've discussed in the course until now. So if you're worried about the exam, if there's something that's not clear, this is a good, yeah, go ahead.
Is there a possibility that we could go over, like, doing covariance, finding the variance, give an example?
Sure. The question is about examples of covariance. Did you try the homework?
Yeah, so I just, looking at the notes, like, I understand the formulas, but I wasn't sure how to apply it. So, like, given the x, y, or whatever, so applying it through there.
All right, can you give me a specific example? Can you think of a specific exercise? I'm trying to understand where the difficulty is. X is a random variable with how many values? 3, okay. And their values should be -1, 2, and 10. All right? And their probabilities is 0.5, 0.3, and 0.2. This is a perfectly good random variable. What is the mean of this random variable? What is the mean? It is 0.5 times -1 plus 0.3 times 2 plus 0.2 times 10. And I guess I will do it just for the heck of it. So this is negative minus 0.5 plus 0.6, right? Plus 2, this is 2.1. We found the mean. The variance, am I being helpful to anybody with this?
Yes.
Okay, thank you. V of x is defined as the expected value of how x varies from its mean, which here is going to be 2.1, squared of that. Specifically, this expectation means that you take this thing for all the different values of x and you weigh them by how likely this x is. So one way of writing that would be p of x times copying this with x over all values of x. So this is x minus 2.1 squared. So again, we have to go over the three cases. The first case is -1, and its probability is 0.5. So 0.5 times -1 minus 2.1 is minus 2.2 squared. It's -1, it's not -0.1. Thank you. -3.1 squared plus the second possibility has a probability of 0.3 times something else squared, and the something else is you take the 2 and you plug it in here. 2 minus 2.1 is minus 0.1, and then you have the third possibility, 0.2 times the third possibility is 10. 10 minus 2.1 is 7.9 squared. I'm not going to calculate that, but so at least conceptually, the way to calculate variance is first calculate the mean. Fix it. It's a constant now. In this case, it's this constant. Then you have to calculate the expectation of this expression. You should be able to calculate the expectation of any expression. To remind you, the expectation of any function of x is defined as the summation over all possible values of x of this function weighted by how likely it is. How likely is this x value? So this function happens to be this function. This is really part of your prerequisites. It would be difficult to move on without having good, good understanding of it. So spend as much time as you need to get it right and to practice it. Yes?
Like a note sheet where we can put formulas, like where we can bring to the first we can bring to the.
You can bring one sheet of paper. I will explain the details online. Yeah?
I have another question. Could you kind of go over OLS and what that kind of meant?
Sure. OLS. OLS comes in when you do linear regression. We use the example of the covariates being your original covariates, but it would also work if the covariates are complicated functions of those covariates, like polynomial regression, like the example I showed before. OLS stands for ordinary least square. Ordinary least square means that you're looking for a solution. It's basically this part. This is OLS. Before you add regularization, if you chose here as a loss function the square of the residuals, this is called the ordinary least square problem. It's least squared. You're trying to minimize the squares. And it's ordinary because you did not modify it in any way. You did not, I don't know exactly why they chose the word ordinary, but you didn't put a regularizer in. You didn't weigh the points differently. There are many, many variations in the regression theory on this. This is like as vanilla as it gets. This is what they start with. Does that answer your question, or should I go into more detail? Okay. Sir.
So you talked about that correlation is rotation in your previous talk, but you predicted that. The examples in your notes, I couldn't get them. Satisfactory answer for that. So one of the examples is examples of high mutual information where correlation is 0. Uniform distribution on the vertices of an equilateral triangle. How is that?
Okay. I'm glad you're reading them. That's wonderful. Let me take the equilateral triangle and put it on the origin. It would be here, here and here. Is that equilateral? I'm trying to create a equilateral triangle with the center as its center of gravity. First, let me explain what I mean by this distribution. I mean that this is a discrete distribution in 2 dimensions, x and y, with point masses sitting here. So there's, let's say, a third probability of being in these points. So this is distribution in 2 dimensions, but it has only 3 points. Okay? The center of mass of this distribution is in the origin. This distribution does not have a preferred direction because there is a 3-way symmetry. If you said the preferred direction is this way, I would say, why not that way? This is a hand-waving argument, but you can calculate mathematically that the linear correlation is 0. It may be harder to calculate mathematically, but because of the symmetry, I can look at it and say there's no preferred direction. There has to be a preferred direction for correlation to be non-zero. There's no preferred directions, correlation is 0. So rho is 0. Now, what is the mutual information? Let me redraw it a little bit so they're not right directly on top of each other. This is here and this is here. What is mutual information between x and y? So this is correlation between x and y. 0. What is mutual information between x and y? What is the entropy of x?
1 by 3 log 1 by 3 times 3.
Entropy of x is the entropy of the distribution 1/3, 1/3, 1/3. Remember, entropy doesn't care what the actual values are, just that they are distinct and what their probabilities are. And this is distinct lines, distinct points. You know, x is here and here and here. 3 different points, each with the third probability. What is the entropy of y? It's the same thing. 3 different points. Here's one y, here's another y, and here's the third y. The projection on the x-axis, on the y-axis. So the entropies are whatever it is for a third. Now, what is the mutual information between x and y? How much does x tell you about y? I'm sorry? Everything. That's right. Everything. Because they are distinct. I tell you the x, you know which point I'm talking about. So these are clearly greater than 0. But the mutual information here is fully equal to h of x, which is also equal to h of y. Another way of saying it is that the conditional entropy of x conditioned on y is 0. If you know x, you know y. If you know y, you know x. This is true no matter what the angle of the triangle is, except when the triangle, one of the lines is either vertical or horizontal. In which case, this is not as extreme, but there's still mutual information. That's true not just for a triangle, it's true for any polygon with equal weights. This is just the example I came up with, but there are many others. Sir?
Could you explain what are the basic assumptions for linear regression, especially in terms of the residues?
So, I'm glad you asked that question. Let me emphasize again, the notion of linear regression or a linear model does not impose any assumption on the residues except that their expectation is 0. The residue random variable has 0 expectation. That's the only assumption of it, which is another way of saying that the expectation of y is a linear combination of the covariates. So the assumptions of the linear model is that, and I would argue that it's just a single assumption, is that E of y is linear in, and here I'm not going to say, I don't want to say x1 through xp because I mentioned that it could be different functions of x1 and xp. In computable features of the input, in the features. And by features I mean some known functions of the original covariates. This is the only assumption. I can write it like this. I can say that the conditional expectation of y conditioned on f1 through fp. So I change my notation a little bit. I now make it dependent on the features. Just to remind you that it doesn't have to be the original axis. But usually in the books you will see just axis here. It means the same thing. You can create new axes, new covariates. Okay? That this expectation is the weighted sum beta j fj. J goes from 0 to p. It goes from 0 because we're assuming that f sub 0 is 1. Just as a notational trick to not carry the offset with me explicitly. This is the only assumption. There's only one assumption. Where does the epsilon come in? If you define, now we define epsilon as the difference between the value of y and the values of these betas, beta j's, fj's. If you define it as the difference, and you say that the expectation of y is this linear combination, then it falls out automatically that the expectation of the difference is 0. Right? Expectation of epsilon is expectation of this minus expectation of this. And by our definition, it's 0. So the assumption of a linearity of the expectation of y is equivalent to the assumption that the residuals, that the expectation of the residual is 0. It only talks about the expectation of the residual being 0, not about the actual shape of that distribution. That's the linear model. That's linear regression. Now, in the most common case, we make the extra assumption that that epsilon distribution, the residual distribution, is Gaussian. That leads to the least square or ordinary least square solution. We could make a different assumption about it. It would lead to a different solution. It will not be the ordinary least square. It would still be linear regression. It'd still be the linear model. Does that answer your question? Mm-hmm. Yes?
So for the OLS case, we've seen that the search is basically there's no search because there is a definitive solution, right?
Right.
But when we have L0 and L1 and L2 in the place, then we need to do a search.
Yes.
How do we go about it?
Wonderful. Wonderful question. So was pointed out to me that when we do ordinary least square with no regularizer, there is really no search because we have a closed form solution. But once we put in regularizers, we no longer have a closed form solution. That's true, and we need to search. How do we do the search? And the answer is quite interesting. The answer for L2 came first. L2, that's ridge regression, that's been known for quite a few decades now. I don't know exactly how many, 3, 4 decades. And the answer there is, I believe, iterative. William, correct me if I'm wrong, is iterative. An iterative procedure, it relies on the fact that both the original loss function and the regularizer are convex. And when you have a convex problem, there are many, many ways to solve it. Convex problems are easy to solve. They have a single global optimum, minimum, and maximum, and you can solve them by gradient descent. You can solve them by like Newton-Raphson kind of method. There are many ways, many algorithms, many different techniques, and they would all get to the solution because there is a single solution. Sometimes you have a closed form solution, many times you don't, but it's not a problem. When the problem is not convex, that's when you have a problem and you have to use heuristics, and sometimes you get good solutions, sometimes you don't. So ridge regression came first. It was a very simple thing to find the maximums. Lasso came relatively recently. I say recently, it's probably, I don't know, 15 years, something like that. And the main observation there was that the likelihood space that looks like this is also convex. It's in the extreme edge of convexity. So the solution in Lasso is also iterative. It's somewhat more complicated, at least conceptually. But what it works by is effectively ordering the covariates in order in which they make a difference and showing a path through them. I mean, that's the most I can do with my hand waving. The short answer is both of them require iterative procedures. But they're both guaranteed to give you the optimal solution. That's an important point. Many times we set these optimization problems, combination of loss function and regularizer, and we look at it and we feel very good about ourselves because we wrote a great expression, but we don't know how to maximize it. We don't know how to find the actual solution or minimize it, how to find the minimal solution. It's still a very useful exercise, A, to help clarify for us what we think is a good solution, and B, to start thinking about heuristics and maybe random searches and other techniques to try to find decent solutions. And certainly if somebody gave you two solutions, you can compare them by calculating for them the value of the loss function, the value of the regularizers, and seeing which one is lower. Okay? So that's an important point, as long as I'm going off on a tangent. In computer science, we make a distinction between finding a solution and verifying a solution. Right? This is the whole difference between P and NP. An easy problem is a problem where you can relatively easily find the best solution, the optimal solution. In optimization cases, sometimes you're not guaranteed to find the optimal solution, but if you can still calculate the value or the merit of any one solution, then you can compare two and say which one is better. And another step beyond that is not only being able to compare two, but to also recognize that one of them is the minimum. That's harder. Here we're in a situation where we can actually calculate, we can find the global maximum. If you change the LP to L0, it's not that we can't, but it's computationally expensive. It's exponentially expensive. But if you give me two solutions, I can easily tell you which one of them is better. Go ahead.
What do you mean by iterative solution when you talk about L1, L2?
What do I mean by the what?
Iterative solution.
Iterative solution. So we will see examples in this course of iterative. It's an iterative algorithm. You start from some starting point, sometimes a random starting point, and you iteratively, by iterations of an algorithm, change your answer, improve your answer. So gradient descent is an iterative algorithm. Here's a gradient ascent. You start here. You calculate the slope of the line based on the value of the direction and the size of the slope. You take a step. You calculate it again, and take another step, and another step, and maybe you get stuck in the local maximum. But you're doing it by iterations.
By solution, you mean the value for beta?
Yes, the best solution, I mean solving the argmax problem or the argmin problem. So whenever you see the word argmin or argmax, that's called an optimization problem, and you can think, oh, that's a search. I need to at least conceptually search the space of betas. Sometimes I don't need to search, as you pointed out. I know what the answer is. most real-world situations, you will need to search. And then the question is the solution, is the value of what comes after this convex in the parameters that I'm searching over? If it is, whew, I know there's a single global optimum, and I know there are 50 ways of finding it. If there isn't, then starts the hard work. Yes?
Decision trees, we were saying that like the soft bias was like trying to restrict the number of nodes sometimes, right? But then our greedy algorithm didn't necessarily find the thing with the smallest amount of nodes. Does that mean that the soft bias changes the things that are representable that way? Or does that just mean that actually doesn't necessarily find the best thing?
Wonderful, wonderful question. Let me repeat it. In decision trees, the kind of soft bias that we introduced had to do with the number of nodes, trying to keep them small. Let me slightly correct you. You said that restricting the number of nodes. If we restricted the number of nodes, that would be a hard bias. But preferring trees with smaller number of nodes would be a soft bias. But then, as we built the tree, we acknowledged that even if we try to find the smallest tree that agrees with the training data, our method is greedy. It's not an exhaustive search of all trees of a certain size. Our method is greedy, and as a result, we may not find the smallest tree. And the question is, does that mean we effectively changed our soft bias? Or, I don't know what the other thing is, but I buy that answer. Yes, I think we did effectively change if we stick to the algorithm, then we effectively changed our soft bias, because if there is a shorter tree, we're not going to get to it. Now it's up to how you like to view things. You can even say that if the algorithm makes you miss a tree completely, then it's kind of like a hard bias, because you're no longer, but it's not a hard bias of decision trees per se, it's of the particular algorithm. It's in your eyes how you want to term it, but I think you're thinking about it is very, very right. Yeah?
So going off of this, so is hard bias and soft bias something that's, like, it seems like something that's almost up to interpretation, so like,
almost what?
Up to interpretation, because in that case, it's completely exclude a solution, so it's no longer a ranking. Because like in soft bias, I guess, is more of a heuristic which you use to find things quicker. But if you're still doing a search of the whole space, you should still be able to find the maximum, if the maximum exists, right, or if optimal exists. So like, regardless of your soft bias, you should always be able to find the optimal solution, right? But the moment you can't find the optimal solution, it becomes more of a hard bias, right? Because you're restricting the set of possible solutions, and that changes whatever your optimal solution is. So is that the way to think about hard bias?
I think it's a wonderful way to think about it. Let me repeat it for the benefit of the tape. The observation was that the hard bias versus soft bias is sometimes a matter of interpretation. And I think it's true, just like it's true for just about any other concept in human life. Once you look at it really, really closely, sometimes there are border cases that, it's up to you if you decide to call it this or that. But the essence of the distinction I try to make with hard bias and soft bias is one of them has to do with, can you even represent something? Is it in the space that you are in principle searching? Is it expressible? And that would be the hard bias. And the second one, and as opposed to it's there, but you're not likely to get to it, that would be a soft bias. The other way you put it is that if you have a chance of getting to it somehow, then it's within your hard bias, within your expressive power. Yeah, it's kind of up to you, but in most cases it's pretty clear. You create a certain representation, and by creating that representation, you eliminated a large part of the possible solutions. Okay, go ahead.
So I was like confused when I was like reading the note. Could you give us some like real examples of like mutual information of like 3 random variables or 2 random variables both being negative?
Two random variables mutual information cannot be negative.
I mean, like when you're like focusing on specific y instead of.
So I thought did I not give here the example of one variable being the XOR of the other two?
You did.
Okay. Okay. So go back and look at the lecture If you don't like the way I describe it this year, go back and look at how I described it last year. But if it still doesn't make sense to you, please come see us. Sir.
I have a question about the how you reach the conclusion that the distribution of the residue is actually a Gaussian distribution. Because previously I didn't got this conclusion in your way, because I proved this by saying that only when the distribution of the residue is a Gaussian distribution that your linear function will be an unbiased estimation of your data set. So
Okay. I did not, you're asking about how did I get from the assumption of the residuals being Gaussian to this minimizing the square, some of the squares. We're jumping ahead a little bit because that's planned for the second part of the course, but since we are doing whatever you guys want, then I'll do it. It's not very hard. I'll at least give you the flavor of it. It has to do with viewing the expression there, the loss, as the log likelihood. Okay? Log likelihood of your data. I'm going to keep it a little bit hand-wavy, but I want you to see the main mathematical relationship. The likelihood of an epsilon, if it came from a Gaussian with mean 0 and some standard deviation, is 1 over 2 pi standard deviation. Or is it like this? I never remember. Think not. E to the negative epsilon squared over 2 sigma squared. The likelihood of epsilon 1 through epsilon n, according to this, is a product of 1 over 2 pi sigma e to the negative epsilon I squared over 2 sigma squared. This is the expression for a Gaussian. Now, if you take the log likelihood, log of this likelihood, this becomes a sum. This thing is a constant. It won't matter for the optimization. We'll cross it out. This becomes a sum of the log of this. What is the log of this? It's negative epsilon squared over 2 sigma squared. Maximizing the likelihood is the same as maximizing the log likelihood. Maximizing the log likelihood is the same as maximizing this, which is the same as minimizing this. And again, this is a constant. So if you were looking for what does Gaussian have to do with sum of squares, go to the definition of a Gaussian, look at what it says. It's e to the power of something squared. It's that thing, that squared that's there, that's doing that. We're going to talk later about, about the relationships between log likelihood and loss function. Thank you. We'll see you tomorrow evening.